Welcome to homework.
Formula C5H9ClO2, and we are asked to deduce the structure of P from its proton and carbon NMR spectra. And so those spectra are pictured just below the problem. And so what I've done is just write out the proton peaks here on the left. And then from the carbon NMR, all that we really need to see is that there are 5 signals. So we have 5 distinct carbons. There's no symmetry or identical carbons in this molecule. And then the other thing to note is that the signal at about 170 ppm is telling us that we have a carbon that is part of a carbonyl. So that's a useful piece of information. And that's about all that we can get out of the carbon NMR there. So the first thing I like to do in this type of situation where we have a formula and we are asked to find a structure, I like to start by calculating the HDI. And so for this molecule, it's going to be 2 times 5 plus 2 minus 9 for the hydrogens, and then minus 1 more, because remember, we need to subtract 1 for each halogen that we have, and we do have a chlorine here. And so then all of that is going to be over 2. And so it ends up being 2 over 2, which is 1. So we have 1 degree of unsaturation in this molecule. And of course, that agrees with the carbonyl that we just identified from the carbon NMR. So that's going to account for our single degree of unsaturation. Okay, so next we need to look at the proton NMR. And the way that I like to do this is to try to figure out what each of these signals represents. So we have at 1.4 ppm a triplet that integrates to 3. And that integration of 3 is a pretty good clue that that's a methyl group. And then all 3 of these other signals integrate to 2. And so they are going to be methylene groups. But there is a little more information that we can get here. So all 3 of these are methylene groups. However, 2 of them are split to triplets, and the third one, the signal at 4.2 ppm, is split to a quartet. And so that's important because that tells us that that methylene group is next to this methyl group. So the methyl group, the signal at 1.4 ppm is split to a triplet. That means it has 2 neighbors. And the signal at 4.2 ppm is split to a quartet, which means that it has 3 neighboring protons. And so it's a safe assumption that those 2 signals are splitting each other here. And so we know that one side of our molecule is going to be CH2CH3. Okay, and so our other 2 signals at 2.8 and 3.8 roughly ppm, they're both triplets, and they both integrate to 2. And so I'm going to say that the one at 3.8 ppm is going to be our methylene group that has the chlorine attached to it, because it's further downfield and chlorine is electronegative. So also looking at this formula, we have 2 oxygens to account for, and the chemical shift of the 4th signal at 4.2 ppm is pretty far downfield. So I'm going to say that this is an ester, and we have our ester oxygen there, and then we have our ester carbonyl, And so that accounts for the chemical shift of 4.2 for that one methylene group. And then I'm going to say that the other side of this molecule looks like this. So CH2, CH2Cl. Okay, and so again, the methyl group is obvious, which is the methyl group. But of these three methylene groups, this red arrowed one is going to be this. The blue arrowed methylene group, as I said, since it is further downfield, that's going to be the one with the chlorine attached to it. So that'll be that one. And then the black arrowed methylene group is going to be this one right here. And 2.8 is a pretty good chemical shift as well. But just comparing 2.8 to 3.8, 2.8 is more likely to be alpha to a carbonyl, which this one is, and 3.8 is more likely to actually have the highly electronegative chlorine directly attached to it. And so this is the answer here. This molecule I've drawn in green to the bottom right. And again, the arrows are just serving to clarify which signals are coming from which groups. And that's the answer to chapter 14, problem number 69.